So I'm not sure how many people are actually going to watch this video because it's more a response to a conversation I'm having on Math Overflow. This actually has to do with my research. I don't know, maybe some of you are interested, but I'm going to jump like right into the thick of things. And so if you don't happen to be working in the local language program, maybe this doesn't make a ton of sense to you. I don't know. But I wanted to make this video because maybe it'll be easier for me to express my own thoughts and confusion. So you can read this post I made. It's a question I have. I'll put the link in the description. But basically I am asking, for p-adic groups, there seems to be the claim, or at least implicit assumption in a number of different papers that I've looked at, that that parabolic induction corresponds to tensoring. Well, you have adjunctions on either side corresponding to induction from either parabolic, and this should correspond to either the tensor product or this Hom functor on the level of the Iwahori or affine-Hecke algebras, right? So I have this question, give some sources, and then Stefan, who actually I know. So hi, Stefan, if you're watching this. Stefan's a good dude. We were in an online class together that my supervisor taught in a previous year. Anyways, irrelevant information for anyone else watching this, I guess, but. So they point out this paper of Hellman, which I think, do I have open here? Yeah, and where's that diagram? So they mentioned that this question I have follows from a diagram of Hellman, and actually I think this would be a slick argument. So that one, or an easier argument, is to actually approach it by showing this commutivity where we actually use the Jacquet functor and the forgetful functor, right? But part of the problem is here, this forgetful functor is coming from this embedding from the Hecke algebra. I'm going to go over some of these definitions in a second, right? That the Hecke algebra here, but I mean, what is this embedding? Like, so Hellman doesn't say. He says there is a canonical embedding, but he doesn't say what this embedding is. Okay, I believe I do understand, like as per one of Stefan's later comments, down here about how you embed one into the other. The problem is that's a different version of the Hecke algebras. Let me explain. Let me make some diagrams and explain my thought process here. So, where's my pen? There we go. Things are just moving a little slow. So what Hellman calls H sub G, right? He defines this to be the endomorphism algebra. So this is G representations. So we're going to take compact induction. Oh, sorry, my computer is being really slow and bugging out right now, and that is making the drawing very annoying. So it's going to be compact induction from the Iwahori subgroup up to G of I. Yeah. And in this case, we get, and so this should be isomorphic to what people normally call the Iwahori-Hecke algebra. So maybe H, comma, GI, where this is, compactly supported, locally constant functions, which are bi-invariant, complex valued functions, right? So these two incarnations of these algebras should be isomorphic, right? They're isomorphic algebras. And in either case, we get an equivalence of categories. So, for example, we get, if we take the category of G representations, and I'm not sure if there's actually a difference between if you stipulate that each of the irreducible factors has to have an Iwahori fixed vector, or if it's just there exists a single, at least one non-zero vector, which is fixed by the Iwahori subgroup. But in either case, we have an equivalence of the categories, category of representations. Well, we have two equivalences, right? We have the first equivalence is sort of the traditional one, if you will, defined by intertwining integrals. Or, I mean, you integrate, a function acts by basically integration. If you look at a standard source on this, if anyone's watching and wants to know, I mean, I'll give you the sources. Let me know. But then we also have another equivalence. So this is equivalence of HGI modules, and we have another equivalence from this category to HG modules. Both essentially boil down to the underlying under these equivalences, the underlying vector space. You take the I fixed points of the vector space, but there's two different actions here, right? So here, I guess I'll just show it to you. The action is this integral I said. So a function in here acts by integrating, right? Integrating over all these actions. Down here, the way you actually set up the I fixed vectors is you take like the Hom space from this compact induction into your vector space, ends up giving you the I fixed points. But then the point is, of course, the endomorphism algebra acts by precomposition on this factor, right? But so we have two equivalences of categories, right? But relevant to my concerns are that if you put the equality here, it's not clear that, so we have an isomorphism. There could be many different isomorphisms between these algebras, and then any morphism of algebras induces a triple adjunction of functors between the module categories, right? And so it matters what isomorphism you pick between these two algebras, right? It's not so clear that if you have an isomorphism, going one way, that this induces whatever isomorphism you've picked, that induces an equivalence of categories here that specifically commutes with this particular diagram, right? So I guess my concern is this, like if you take, so there's other versions. So we have, for example, I'm going to call this math face bold HGI. There's sort of this presentation of a free module with a certain basis of generators and relations. I think this is the Bernstein-Lustig presentation. So this is isomorphic to both of these other incarnations of the Iwahori-Hecke algebra, right? And in this incarnation, which is essentially, Stefan's comment, it is actually, relatively clear to see the embedding that you get here, right? And so that induces an HG module structure, or sorry, an HM module structure on HG, right? But then, ultimately our goal is to sort of prove this commuting diagram that shows up in Hellman's work, right? But Hellman's working specifically HG, right? So the embedding, whatever embedding that you get here, HM into HG, I mean, that embedding depends on the isomorphisms that you're putting here. And the isomorphisms that you put here also affect, like if it affects the embedding, that means it affects the HM module structure on HG. And so that's also going to affect the like tensor products or the restriction map that you use, right? So it depends on a bunch of things. And there's more to prove in this diagram. Let me go back to this diagram, right? Like one needs to check that we actually have an intertwining map, that if we go either way around this diagram, the HM module we end up with, like, it depends on the particular module action we're using, that we actually have an isomorphism up in this corner, right? And then like the other thing that's not clear to me, so there's these isomorphisms floating around that are just like, it's not checked here, it's not talked about here, or in like these other papers of Soloveld that were mentioned. And then on top of all of this, like if we just think about this diagram, in order to get this commutivity, say so we've got rep GI, and then Jacquet should take us down to rep MI, and we should also get this equivalence over to so here's HM mod, and this involves on the underlying space taking the Iwahori fixed points and HG mod, and then we have this sort of mysterious restriction here that we don't know explicitly because it depends on our choice of embedding. So I mean, if we start with some representation with an I fixed vector, I mean, it's not even clear to me the map that we get on the underlying spaces, right? You go one way, you take the I fixed points of V, right? If we're going this way around the diagram, and then we just take restriction, so the underlying space will be the same. But if we go this way, right, we're taking the Jacquet module of N. So this is basically, V mod the V invariance. And then we're applying the IM fixed points, right? So then we get, JV IM, which is just intersecting the Iwahori subgroup with M. So we go here, right? But, like I claim it's not so clear what map should intertwine these underlying spaces, right? So certainly, if you are I fixed, you're going to be IM fixed, right? And if you're IM fixed, you're definitely going to be an IM fixed point of this thing, right? So by including into here and then projecting down through Jacquet, right? This should live inside here, right? So we get a map, but it's not even clear to me that there should be an isomorphism, right? Like if you think about unpacking J V, the IM fixed points, well, what does it mean to be IM fixed? This says that pi k V plus this coset, these cosets are fixed for all k in IM, right? So in other words, pi k V minus V is in Vn for all k IM, right? That's basically the condition on this space, but that seems like a very different condition than this, right? So probably it's some sort of like intertwining integral. So like even to get the right map on the underlying spaces, it seems like there's a lot of work to be done here that I just don't think is written down anywhere. And then we also need this intertwining map. I mean, maybe I'm missing something like very obvious, but yeah, that's it. That's something I'm thinking about right now.